In this lesson, we're going to look at solving systems of equations using the elimination method. So let's look at our key terms. The elimination method for solving systems of equations makes use of the addition principle. To eliminate a variable when adding, the terms containing that variable must be opposites. When solving using the elimination method, obtaining a false equation means there is no solution. And when solving using the elimination method, obtaining a true equation, it means the system has infinite number of solutions. So let's look at how the elimination method. This system you could solve using substitution very easily by isolating one of your variables, but it's set up perfectly for the elimination method, so that's what we're going to look at. In the elimination method, you literally add your two equations together, and in hopes of one of your variables canceling, and that happens if you have opposite leading coefficients. So here if I add x and x, I get 2x, so that didn't eliminate, but when I add negative y plus y, those do eliminate. And 3 and 11 is 14. So I'm given a mini equation to solve. So it looks like x equals 7. Had those not canceled, then we would have had to do something different to help eliminate. It's called the elimination method because when you add two equations together, you want one of your variables to eliminate. So just like in substitution, we are still looking for the intersection point of our two equations, or two lines. So we have half of our answer. So x equals 7, so we've got to find the y that goes along with that. And to do that, just pick one of your equations. It doesn't matter which one. I'll just pick the bottom one. X plus y equals 11. Since I think x is 7, I plug in my 7 and solve for y. So it looks like I get y equals 4. So 7, 4 would be my final answer to this system. And again, we could have solved it using substitution method. It's whatever method you prefer. Some systems lend themselves to substitution method easily, and some are set up beautifully for elimination. So it just depends on what the system looks like as to which method you will use to solve it. So here we have another system, and you probably notice that if I add my two equations together, I have r and 3r, I get 4r, so they don't eliminate. S and a minus 2s, if I add those together, the s's will not eliminate. So that's not going to do us any good. So we're actually going to have to use some multiplication prior to using our addition for elimination. So what I'm going to do is I'm going to take my top equation, and you can decide, do you want to eliminate r's or s's? And either one will be fine. I notice that my s's are already opposite signs. One's a positive, one's a negative. So wouldn't it be great if in my top equation my s, instead of being just a single s, was a 2s? So we're going to make that happen. If I multiply everything by 2, that gives me 2r plus 2s equals 18. If I bring over this equation, my original, I'm not going to change it at all. Now you can see that when I add, my s's eliminate. So we used multiplication to create a scenario in which we would have opposite coefficients. So now when I add, I get 5r equals 13. Oh, looks like I'm going to end up with a fraction, which is okay. So r equals 13/5. Again, I have half of my solution. Since we're dealing with r and s, think of alphabetical order. So r, that's going to be like my x. And we have to find the y that goes with it. So take one of your original equations. It doesn't matter which one. I'm just going to take the top one. R plus s equals 9. I'm going to replace my r with 13/5. subtract 13/5 from both sides, so S is going to be 32/5. So 13/5, 32/5 is my final answer for this system. Here we have another system. 8a plus 12b equals 10 and 6a plus 9b equals 5. So I don't have really a variable that will eliminate easily. In the last one I could just multiply one of my equations and I would get opposites, but here it doesn't look like I'm going to be able to do that. I think I'm going to actually have to multiply both my equations. So what I'm going to look at is if you want to eliminate, let's say, the a's. Those are smaller numbers, so that's the only reason why I'm looking at my a's. What's the first number that 8 and 6 both go into? And that would be 24. So if I could get one of them to be a 24a and the other one to be a negative 24a, then I can get some elimination going. So I'm going to multiply my top equation by 3, and that's going to give me a positive 24. So that means I need a negative 24a in my second equation, which means I'm going to have to multiply all of that by a negative 4 to make that happen. So this is going to give me two new equations, and my a's should be opposites by the time I'm done multiplying. So I'm going to have 24a plus 36b will equal 30. And then my second equation will be negative 24a minus 36b equals negative 20. So now when I go to add my two equations together, 24a minus 24a is 0a, which is just 0. They cancel each other out. And 36b minus 36b, actually those cancel each other out as well. So all I have left on the left-hand side is a 0. All of my variables have been wiped out, and I have equals negative 10. So it's difficult to solve for a variable when your variables cancel out. So what this means is I've got a false statement. So what that tells me is there is actually no solution to this system. Whenever all of your variables cancel out and you're left with a false statement, that means there's no solution, which what that tells me about my two equations is they're actually parallel lines. If I were to manipulate both of those into slope-intercept form, I would end up with parallel lines, so no solution. Again, if we would have eliminated our variables and we were left with a true statement, had this been 0 equals 0, then we would have gotten a true statement, which would have been infinite solutions, which means that our two original equations would have been the same exact line. So these kind of scenarios happen just like when you're graphing. Your lines will either intersect, they'll never intersect, or they will be exactly the same line. This is what happens algebraically when you try to solve a system. Now let's look at a word problem, and let's use systems to solve it. In a recent basketball game, the Westside Wildcats scored 91 of their points on a combination of 41 2- and 3-point baskets. How many of each type of shot were made? So we're going to be writing two equations. Now we're given information about points and we're given information about baskets. So one of our equations is going to be all about the points. So which numbers describe our point situation? Well, we know that we have 2-point and 3-point baskets, so that's going to help us with our setting up our variables. So I'm going to have 2 points for every 2-point basket, and I'm going to have 3 points for every 3-point basket, and the number of points that I will total is 91. So the 2 and the 3 represent 2-pointers and 3-pointers. I have to use two different variables because those are two different values. And now I'm going to look at setting up an equation about just the baskets. So let's see, I've used the number 91 already, and I've used the number of 2 and 3, so the other number I'm left with is 41. Well, baskets, we know that we have 2-point baskets, which I don't know how many of those, and I have 3-point baskets, don't know how many of those, but I know that my total number of baskets is 41. So here's my system I have to solve. Once you set it up, you can solve it substitution, elimination, whichever method you want. Since we're looking at elimination, I'm just going to use that particular method. So I'm going to eliminate, I don't think it matters, how about my x's? Since I have 2x in the top equation, I would like for this equation to be negative 2x. So that's going to give me negative 2x minus 2y equals, it'll be a negative 82. If I bring over my top equation, 2x plus 3y equals 91. So there's my system. My x's eliminate. I'm left with negative y. Oh, sorry, not negative y. 3 minus 2 is 1, so I've got y equals, and 91 minus 82 is 9. So what that 9 represents, okay, y equals 9. Well, y was 3 pointers. So I have 9 3-point baskets. So there's part of my answer. Remember, we want to know how many of each type. So I've got 9 3-pointers. Now we have to find how many 2-pointers. So I'm going to take one of my equations, x plus y equals 41, and I'm going to replace the y with the 9. Subtract 9 from each side, and that's going to give me 32. So it looks like I have 9 3-point and I have 32 2-point baskets. So there's my two answers, 32 2-points and 9 3-pointers.